Hello everyone. This is the last video on solid state, and this is solid state video number 25. And in this video, I'm going to discuss some important numericals on ionic solids, and also here numericals on defects. So whenever solids have Schottky defects or Frenkel defects, or it may be impurity defect, whatever it may be, and what kind of questions can be asked and how to solve those questions, even some questions on a diamond kind of solids, what kind of questions generally there is a possibility for asking, and how to solve those questions we are going to discuss in this video. And first, before going to the numericals directly, let us try to recollect some information, so here related to ionic solids. So here in general, uh, after studying all ionic solids in detail, and what are the important points you have to remember? The important points you have to remember, if you take rock salt type of structure, so here anion is present at face center and corner. Anion is present at face center and corner. That means anion forms FCC lattice, and cations occupy all octahedral voids, and the coordination number values, so that is 6 and 6, hence the type of packing is 6:6, and each unit cell has 4 ionic pairs. But for very sure, these are not memory based points. So if you can remember this information, like which is forming lattice and which is occupying the voids, so based on that, every parameter can be developed very easily. So here this is about rock salt type. In case of cesium chloride type, so here position of anion, if anion is at a corner, then cation will be what we call body center. In fact, that is called cubic void. If anion is at body center, then lattice will be formed by cation. That is, cation will form simple cubic lattice. So one ion is forming simple cubic lattice, and another ion is sitting in a cubic void. And the coordination numbers 8 and 8, and each unit cell has only one ionic pair. And the next one is a zinc blend. In case of zinc blend, again anion forms lattice. Which lattice it is forming? FCC lattice. And Zn plus 2 ions, cations occupy 50% of tetrahedral voids, and their coordination numbers, and each unit cell has how many pairs? So here that is 4 pairs. And the next one is Woodsite. Here anion forms a HCP lattice. Instead of FCC lattice, here HCP lattice. And cations occupy 50% of tetrahedral voids, and 4:4 type of packing. And here there will be 6 pairs. HCP lattice, there will be 6 pairs, 6 formula units in one unit cell. And the next one is calcium fluoride. In case of calcium fluoride type, so here this is here, in fact, in case of this column, if you observe, so what did I write here? This is position of anion. Yes, this is calcium fluoride, position of anion. So here anions occupy all tetrahedral voids, and calcium ions are forming the lattice. Which lattice? FCC lattice. So always first we have to write the coordination number of cation. So cation is present at a face center and corner, and cation is surrounded by 8 tetrahedral voids. So the coordination number of cation is 8. Coordination number of anion is 4. Hence it is 8:4 type of packing. And here there are 4 ionic pairs and antifluoride structure. So here anion is forming the lattice, that is the FCC lattice, and cations occupy all tetrahedral voids. And here the type of packing is 4:8, and there are also 4 pairs. So here in previous videos, with the help of diagrams, we studied everything clearly. But before going to the numericals, I just wanted to remind the positions of various ionic solids, and let us discuss some questions here. So a crystal, that is PBS. The crystal which we are talking about is PBS, and it has NaCl structure. In this, the shortest distance between Pb plus 2 and S minus 2. The shortest distance between Pb plus 2 and S minus 2 means there must be contact between Pb plus 2 and S minus 2. So that is 297 picometers. And what is the volume of that unit cell? What is the volume of that unit cell of PBS? So he's saying that it is NaCl structure. NaCl structure means anion should be present at face centers and corners. So here, and the shortest distance is given. So I have taken edge. If you observe the arrangement of Pb plus 2 and S minus 2 along the edge, so here this is corner, and this is edge center. And in fact, the shortest distance between Pb plus 2 and S minus 2 means this value he gave. This value he gave, that is A by 2. A by 2 is 297 and A will be 594, double of that. And since it is a cubic unit cell, volume is equal to AQ. A very simple question. So volume of the unit cell is equal to AQ. So like that we can find. So already I told you we are not focusing on the simplification part and how to link the data. That is our discussion. And the next one, cadmium oxide has NaCl structure. Density is given as 8.27 gram per cc. Ionic radius of oxide is also given, that is 1.24 angstroms. Find the ionic radius of cadmium plus 2. Again, it is NaCl structure. So we can take what do we call the arrangement of particles along the edge. In that situation, each edge has 2 anions and 1 cation. And if you can find the value of edge length, you can easily find the radius of cadmium plus 2. But here edge length is not given. Instead of edge length, he gave what do we call ionic radius of oxide ion he gave. So what we have to do, with the help of this density, let us try to find edge length. With the help of this density, let us try to find the edge length. Simply I have to use the density formula, and the cadmium atomic mass is also given. NaCl structure means there will be 4 ionic pairs. So density is equal to Z effective into formula mass of cadmium oxide. Cadmium is 112, oxygen is 16, that is becoming 128 by Avogadro number, and you will be getting edge length cube, that is volume of the unit cell. And if you simplify, you will be getting edge length value 4.68 angstroms, right? And what is our requirement here? Ionic radius of cadmium plus 2. In the same diagram I have to take, and this distance is edge length, and this edge length is equal to 2 times of radius of cation plus radius of anion. So this is anionic radius, this is anionic radius, and in fact this is diameter. So that is 2 times of radius of cation. So oxide ion radius is given, and from this you can easily find the radius of cadmium plus 2, and you will be getting it as 1.1 angstroms. 1.1 angstroms. So that is the radius of cadmium plus 2. And the next one, potassium chloride crystallizes in the same type of lattice as NaCl, of course. So NaCl structure and KCl structure, both the structures are same, that is he's saying. And radius ratio of sodium chloride is 0.5. Radius ratio of sodium chloride is given as 0.5. And radius of Na plus by radius of K plus is given as 0.7. Find the ratio of side of the unit cell for KCl to that of NaCl. Simply what he's asking, edge length of KCl and edge length of NaCl ratio he's asking. With the help of given data, you need to find edge length ratio. Which type of unit cell it is? NaCl type of unit cell. Simply, very simple, you just write the formula, you'll get the idea. So edge length of KCl by edge length of NaCl, in fact, that was asked in this question. And since it is NaCl type of unit cell, edge length is 2 times of radius of cation plus radius of anion. Here also 2 times of radius of Na plus ion plus radius of Cl minus ion, and we have these ratios. And here we have Na plus ion, here also we have Na plus ion. So what I suggest is try to write every radius in terms of Na plus. That is the only way you have to calculate, because in this ratio we have Na plus, in this ratio also we have Na plus. So what I have to do is, in place of K plus, I have to write the radius of K plus in terms of Na plus, and of course Cl also in terms of Na plus. This is already in terms of Na plus. This is also in terms of Na plus. So in place of radius of K plus, bring this 0.7 this side and K plus this side, and you will be getting, so radius of Na plus by 0.7. And in place of radius of chloride ion, bring this chloride ion this side and 0.5 this side, you'll be getting radius of Na plus by 0.5. Here already we have radius of Na plus. This is radius of Na plus by radius of 0.5, and 2 and 2 are getting cancelled, and of course the simplification part. I already told you I will be helping only in linking the concept. I don't want to waste the student time here. So here just how to link the concept, that is my discussion. So you will be getting edge length ratio will be 1.143, right? And next let us take magnesium oxide, again NaCl structure, and radius of magnesium plus 2 is given as 0.86. Radius of oxide is given as 1.24 angstroms. Find the density of magnesium oxide solid. Here radius of cation and radius of anion information is given. Very good. Type of structure is given, of course, good. And he's asking density. Density formula you know how to find. NaCl structure means Z effective will be 4 ionic pairs will be present. But the thing is, you see radius of cation by radius of anion, if you simplify this, the ratio will be slightly greater than 0.414. If you can recollect here, this is host, means oxide ions are present at face centers and corners, and Mg plus 2 ions will be in all octahedral voids. Octahedral void means what is the radius ratio? What is the radius of octahedral void? 0.414 times of radius of anion. But here the radius of Mg plus 2 is slightly greater when compared to 0.414 times of radius of anion. That means there is a slight distortion. There is a slight distortion. Hence, you should not use root 2a is equal to radius of anion. If you use that formula, so your answer will be slightly different, because here distortion is taking place. But that's why you have to use this relation, that is edge length is 2 times of radius of cation plus radius of anion, and edge length is equal to 4.2, of course, angstrom units. This is in angstrom units, and the question is about density. So density is equal to Z effective. So 4 ionic pairs. Magnesium oxide formula mass is 40 because magnesium is 24, oxygen is 16, Avogadro number A cube, edge length we got it as 4.2. I converted that into centimeters, 4.2 into 10 power minus 8 whole cube, and ultimately you'll be getting the density 3.6 gram per cc. 3.6 gram per cc. So here that is one question, and the next one, let us move on to the next question. Sulfide of cobalt metal has cubic structure with 4 formula weights per unit cell. We don't know whether it is a zinc blend or a NaCl type, but here he clearly mentioned 4 formula weights, 4 ionic pairs are present. And the density of that solid is given, that is 4.269 gram per cc. And the edge length is also given, that is 6.93 angstroms. Edge length is also given. Straight away, edge length is given. Find the mass of sulfur required to produce 1.5 kg of this compound. We don't know the formula of the compound, but he is asking us to calculate the mass of sulfur required to produce 1.5 kg of that compound. So first we need to predict the formula of the solid. If you can predict the formula of the solid, it will be very easy to find the mass of sulfur required. Here the atomic mass of atomic weight of cobalt is given, that is 59. And he is also saying that there are 4 formula weights per unit cell. We have density, indirectly we have volume. Can't you find the molecular weight, formula weight of that? Easily we can find, because he is saying 4 formula weights, and first you find the formula weight of that, and after getting the formula weight, easily you can predict what is the actual formula, what is the valency of cobalt in this we can find. See, density of the solid is given. Density is equal to Z effective into formula weight by Avogadro number into A cube. So here A is 6.93 angstroms, 10 power minus 8 whole cube. So if you simplify, you will be getting the formula weight 214. What is the formula weight you are getting? 214. Do you know the valency oxidation state of cobalt here? No, in fact, that's what I'm going to find. So the oxidation state or valency of cobalt, I'm taking it as X. Sulfide, when sulfur combines with metals, mostly it is -2. So here sulfide, so this is -2. I mean valency is 2. Crisscross rule if you apply, you got the formula. What is the formula? CO2SX. Alright. Now, what is the molecular weight? 214. What is the meaning of molecular weight or formula weight? It is the weight of sum of the atomic weights of all elements present in one formula unit. What is one formula unit? CO2SX. What is the cobalt atomic mass given in the question? 59, right? So this 214 is equal to 2 into 59 plus atomic mass of sulfur is 32. 32 into X. And X value we got it as 3. So the molecular formula of the compound is CO2S3. But now this is solid state question. Now the second part is a stoichiometric question. And he's asking how much amount of sulfur is required to prepare 1500 grams of that solid. And you see, here you see the molecular mass is how much? 214. In that, this is the mass of cobalt. And this is the mass of sulfur. What is X value? 3. 32 into 3. 96. If you take 96 grams of sulfur, you can get 214 grams of the solid. Got it? Because every 214 grams of salt, 96 grams of sulfur is present. So 214 grams of CO2S3, if you want, you need to take 960 grams of sulfur. But what is the question? He's asking, in order to prepare 1500 grams of solid, how much sulfur is required? That is the question. So the weight of sulfur required will be 673 grams. So this is one question. Here there are two concepts. One is a solid state, another one is a stoichiometry. So you need to catch the logic. If concepts are clear, if you can recollect the formula fastly, easily you can solve the question. Now let us move on to the next question. A sample of iron oxide contained 96.1% of total iron as Fe plus 2 and remaining is Fe plus 3. Find the exact formula of the compound. So here I'm just giving a simple logic. whenever you come across these non-stoichiometric solids, better use simple logic, that is electrical neutrality. Electrical neutrality. So those solids, those salts are electrically neutral. We just use that logic. And what does it mean and how to use? Let me explain. See, 96.1% of total iron has Fe plus 2. Let us assume there are 100 irons. In that 96.1 irons are in plus 2 state and remaining are in plus 3 state. Now, the total positive charge, 96.1 into 2, that is because of ferrous, and 100 minus 96.1 means that is 3.9 into iron plus 3. So what is the total charge you are getting? 203.9, approximately you can take it as 204, no issue, 204. And the total negative charge should also be 204, undoubtedly, because electrically neutral ultimately. And who is anion here? Oxide. What is the charge possessed by each oxygen here? -2. What is the total negative charge it should carry? 204. 203.9, approximately, let us take 204. And each oxygen is carrying how much charge? -2. So in order to carry this amount of negative charge, how many oxygens are required? 102 oxygens, nearly 101.95, 102 oxygens. Because the total cationic charge and anionic charge must be same. The salts are electrically neutral. So how many irons have taken? 100. How many oxygens you are getting? 101.95. And of course, this is correct. According to the options, you have to proceed. And you can also convert that into like this. You can also convert that into like this. So here, 100, and this is 101. That means for every 100 irons, there are 102, let us say, 102 oxygens. So that means for 102 oxygens, there are 100 irons. For 100 oxygens, how many irons? You'll be getting this formula also. According to the options, you can proceed. So here the next one. Edge length of solid sodium chloride is given 563.8 picometers, and its density is given. Find the formula of the compound. So solid sodium chloride, we know the formula. Why is he asking? That means there must be some defect. That's why he's asking. And he also given the information. You see, the difference between the calculated and accurate formula weight is due to crystal defect in which cation is excess. Cation is excess of cations. The defect is due to excess of cations. So sodium and chlorine both are not same in number. And this is the edge length, and this is what do we call density. So what you have to do is, you know, the actual formula weight of sodium chloride is 58.5. Now you calculate the formula weight of sodium chloride by using this data, right? And the difference also he suggested, he stated that excess of cations. So first I'm finding molar mass of formula mass of sodium chloride according to the given data. So density is given. Of course, FCC unit cell, 100% there will be 4 ionic pairs. 4 ionic pairs means Z effective is 4. And the formula mass according to the given data I'm finding, Avogadro number, and this is edge length is 563.8 picometers. So here like this. And ultimately I got formula mass as 58.42. What is the expected value? 58.5, 58.42. And the difference is due to which is excess? Cation excess of cations. So here let us take a sodium, chlorine, and here NaClX I'm taking. And 100% you have to see that sodium must be excess when compared to chlorine, because that was mentioned very clearly in the question, right? But if you write a sodium 0.997 and a chlorine, definitely that is wrong. So that's why sodium is 23. And how many chlorides? I don't know. So let me take and here 23 and chlorine is 35.5, and the formula mass we got is 58.42, and if you simplify you'll be getting X value. What is X value? Effective number of chlorines. So the formula of the solid will be like this, right? This is due to the defect, right? And the next one. So iron oxide crystallizes in NaCl type of crystal lattice. NaCl, let me underline. The crystals, however, are always non-stoichiometric. Let me underline. And the deficient in iron deficiency. Some cation sites are vacant and some contain Fe+3 ions. But the combination is such that structure is electrically neutral. Electrically neutral. Formula approximates to iron 0.95O. I already told you, whenever you get a non-stoichiometric solid or defect, 100% you have to proceed through electrical neutrality. And what is the ratio of Fe+2 to Fe+3 in the solid? That is the first question. And what percent of cation sites are vacant? Here, he's saying that some cation sites are vacant. And how many cation sites are vacant? Actually, NaCl structure he's saying no. NaCl structure he's saying. Very good. And Na plus ions, what is the position of cation? Body center and edge center. Originally, how many sites? Finally, how many sites are vacant? You have to find the percentage. So first, let us find Fe+2 to Fe+3 ratio. And I told you already, electrical neutrality is the key point I'm using. And this is the given formula. Nothing wrong. Write that formula like this. Instead of fractions, let us take the whole numbers. So iron 95, finally, right? This is finally, not initial formula. Finally, this is the formula, right? So 95 irons and 100 oxygens. But we know in this, some of them are in +2 state and the remaining are in +3 state. How many are in +3 state? X. 95 minus X will be in which state? +2 state. And how many oxygens are there? 100. What is the total negative charge? -200. Now, the total positive charge of these 95 irons must be +200. So, X into 3 plus 95 minus X in 95 minus X into 2, the total ferric ion charge, total ferrous ion charge is equal to +200. And from this, you are going to get X value 10. In fact, here only we are getting the answer because he has not asked percentage actually. Need to calculate the percentage ratio he is asking. So Fe+3, 10. Fe+2 will be 85. And the question is like ferrous ion to ferric ions. So ferrous ions 85, ferric ions 10, and you will be getting 8.5. The first question is over. But what is the second question? Sorry. What percent of cation sites are vacant? You see once again, out of 95 irons, 95 minus X, 85 Fe+2 ions and 10 Fe+3 ions. And what is the percentage of cationic sites? Vacancy percentage. So initially, if there is no defect, actually it has defect and the formula has changed to Fe95O100, right? If there is no defect, this will be the formula because he said NaCl type structure, no? If there is no defect, there must be 100 cationic sites. I'm writing CS, cationic sites. How many? 100 if there is no defect. But according to the given formula, the structure, according to the given data, the formula is Fe95O100. In that 95, how many Fe+2 ions are present? How many Fe+2 ions? 85. We are expecting 100, but only 85 are there. What about remaining 15? Initially produced holes, cationic vacancy sites. Cationic vacancy sites, how many? 15. But 10 Fe plus 3 ions are there. You can see 10 Fe plus 3 ions to maintain electrical neutrality, whatever it may be. 10 Fe plus 3 ions. These 10 Fe plus 3 ions will occupy only 10 sites. Actually, how many sites were produced? 15. How many are occupied? 10. How many sites are remained vacant? 5. We got the answer. So 15 holes are produced initially because 85 Fe plus 2 ions out of 100. And but 10 Fe plus 3 ions occupy 10 holes out of 15. So 5 holes remain unoccupied. But he is asking percentage unoccupied sites. How many? 5 out of 100. So that is 5%. So conceptually, if you are good, easily you can solve these questions, right? So this is also almost the same model. So I don't want to discuss this question. So here almost the same model, same thing, but here he's also asking something like density after getting the formula. And let us take the next one. Radius of Mn plus 2 is 0.08 nanometers and that of sulfide is 0.184 nanometers. Predict the structure of the cubic unit cell of MnS solid. Also find the packing fraction. We have to predict what type of structure it is. The very simple logic, and first finding the limiting radius. If you find the limiting radius, you are getting 0.434. Do you remember the data? If the radius ratio is from 0.414 to 0.732, in that situation, the smaller ion will occupy octahedral voids. So it is in octahedral voids. It is in octahedral voids. So obviously sulfide ion is forming FCC lattice and manganese plus 2 ions will occupy octahedral voids. So what is the Z effective? 4. But he's asking packing fraction. Do you remember packing fraction? What is packing fraction? So the volume of all ions by volume of unit cell. Volume of all ions by volume of unit cell. And we are taking ideal calculation concept. And of course, so this is what do we call, how many cations? 4 cations and 4 anions. So here 4 into 4 by 3 pi r c cube. Anions 4 into 4 by 3 pi r a cube. And this is anion is forming the unit cell. Which unit cell? FCC unit cell. Root 2a is equal to 4 times of radius of anion. And from that you can find so what do we call this edge length to volume you can find, and ultimately you'll be getting the packing fraction 0.8. We'll be getting the packing fraction 0.8. So here this is one question, and next one. Yeah, let us solve some questions on Schottky and Frankel defects. If an element atomic weight 50 crystallizes in FCC lattice with edge length 0.5 nanometers, what is the density of unit cell if it has 0.25% of Schottky defects? Avogadro number, we have to use this value. So you need to recollect what is a Schottky defect. Schottky defect is produced due to the missing of some atoms, not migration, due to the missing. So it is an element, atomic mass is given, FCC lattice, and it has 0.25% of Schottky defects. That means due to the missing, what happened? Z effective will decrease. Z effective will decrease. What is the Z effective you have to find? By using that Z effective after Schottky defect, whatever the Z effective you are getting, by using that you have to find what do we call a density. So volume of the unit cell remains the same. Atomic mass remains the same. Due to the missing of some elements, some atoms, effective number of atoms, what happened, decreases. So what is the percentage? 0.25. What is the actual Z effective? 4. If there is no defect. But what percentage? 0.25 percentage. So 4 expected, but this is due to the missing. How much percentage? 0.25% of 4. 0.25% of 4, that is the percentage of Schottky defect. So what is the remaining value? Remaining is 3.99. We are expecting Z effective 4, but due to the given information, according to the given information, Z effective is 3.99. Same thing. Density is equal to Z effective into atomic weight by Avogadro number, and of course edge length is given, and that everything has a substituted in we have substituted everything in a CGS system, and we got the density 2.66 gram per cc. Here you need to understand how to find the Z effective and why Z effective decreases. You should not think about the simplification part. I already told you, once again I'm telling. So you are preparing for a national level examination, right? And now let us move on to the next one. An element X, atomic weight is 24 gram per mole. The edge length of the lattice again given. Observed density is 2.4 into 10 power 3 kilogram per meter cube. Find the percentage occupancy of lattice points by the element. He's asking what is the percentage occupancy. That means there must be some defect. If there is no defect, need not to calculate a percentage occupancy, it should be 100%. But he gave some data, and according to the data, he is asking us to calculate what is the percentage occupancy of lattice points. If there is no defect, percentage occupancy must be 100. But he is asking percentage occupancy means definitely there must be some defect. And which lattice it is? FCC. It is atomic solid, right? What is the Z effective? We are expecting 4. But according to the data, let us calculate. According to the data, let us calculate. This is density. So 2.4 into 10 power 3. So this kilogram is converted into grams. And here we have a meter cube. So 1 meter cube is equal to 1000 liters, and each liter is equal to 1000 centimeter cube. I'll be getting 10 power 6. And I'm finding Z effective from the given data. Atomic mass is given. Avogadro number is 6 into 10 power 23. And this is, what is this? Edge length, yes. And what is the Z effective we got? 3.84. What is the actual Z effective? 4. Actual Z effective is 4. But what is the Z effective we are getting? 3.84. Is asking percentage occupancy. So out of 4, we have only 3.84. So 3.84 is how much percentage of 4? That is the question. So 96%. What about 4%? Defects. It must be Schottky defect and the vacancy defect, of course. Next, calcium crystallizes in face-centered cubic unit cell, FCC. Edge length is given, fine. Density is given, fine. Here, find percentage of Schottky defects in this crystal. Exactly reverse to the previous question. There, percentage occupancy asked. Here, percentage vacancy is asking. That is the only difference. That is the only difference. Again, I have calculated Z effective from the given data, and I got it as 3.84. All right. And that is 96% is occupancy. And here he's asking percentage of Schottky defects will be 4%. Same model actually. Yeah. Let us take the next one. So analysis showed that nickel oxide consists of nickel ion with the 96% of ions D8 configuration, 4% D7 configuration. Give the correct formula of its oxide. See, two different nickel ions. So it must be non-stoichiometric solid. What is the key point? Electrical neutrality. That is the only logic we have. So what is the nickel atomic number? 28. What is the configuration? 4s2 3d8. But what is he saying? D8 configuration means you have to remove these electrons. That means nickel plus 2. D8 configuration, how much percentage? 96 percentage. D7 configuration means if you remove these two electrons, they are not sufficient. You have to remove one electron from this also. Then it will be D7. So totally you're removing 3 electrons. So nickel plus 3, nickel plus 2. This is 96 percentage and this is 4 percentage. And here 2 into 96 and nickel plus 3, 4 percentage, 3 into 4. So we are getting a total positive charge of 204. Total positive charge is 204 means total negative charge must be 204. What is the charge possessed by each oxygen? -2. So in order to have 204 negative charges, 204 negative charges, how many oxygens are required? 102 oxygens are required. So 102 oxygens are carrying the charge -204. So the same logic. So for 102 oxygens, there are 100 nickels. I already told you, you can see 96 plus 4. For 102 oxygens, 100. For 100 oxygens, how many? So you will be getting the formula. Nickel 98 O100, that is Ni 0.98 O1. So that is the procedure. And let us move on to the next question. And calcium crystallizes in FCC with edge length given, and it contains 0.2 percentage of Frankel defects and 0.1% of Schottky defects. Both are present. But the logic is Frankel defect does not change the density. Frankel defect does not change the Z effective. Because Frankel defect means here the particle is migrating from its original site to interstitial site, but it is not leaving. Z effective will not decrease because of Frankel defect. So be careful there. Only Schottky defect will decrease. So Frankel defects do not change density. So Frankel defects do not change Z effective, but Schottky defect decrease density. What percentage? 0.1 percentage. What is FCC unit cell Z effective? 4. So 0.1% of 4. So we are expecting 4, but because of 0.1% of Schottky defects, Z effective has come down to 3.996. Frankel defects do not change. Atomic mass 40, Avogadro number, and this is AQ. And if you simplify, you will be getting the density 1.544 gram per cc. This is also same model. So almost the same model. I'm not discussing. So repeated models I'm not discussing. And let us take in a cubic closest packed structure means CCP of mixed oxides, the lattice is made up of oxide. So oxide ion is host. This host has two types of voids, tetrahedral voids, octahedral voids. Tetrahedral voids are occupied by X plus 2 ions. Octahedral voids are occupied by Y plus 3 ions. Only 50% of octahedral voids are occupied. Then find percentage of tetrahedral voids occupied. Very simple logic. Verification will give the answer. Otherwise, we can also solve. See, X plus 2 is occupied, tetrahedral voids X plus 2, octahedral voids Y plus 3, 50% of octahedral voids. So solid definitely electrically neutral. So how many oxide ions? 4. Y plus 3 ions. are actually present in which voids? Octahedral voids. Octahedral voids are also 4. One body center, 3 edge centers effectively, 4. But he's saying 50% occupancy, so Z effective is 2. But Z effective of X plus 2, we don't know. How many are there? We don't know. That's what we have to find. So X plus 2 ions, how many? I don't know. I'm writing some value A. Y plus 3 ions are 2. O minus 2 ions are 4. And the solid is electrically neutral. You just take the oxidation state. So 2A. So X is plus 2, no? Plus 2. So 2A plus Y is plus 3. 3 into 2, 6. Oxygen minus 2. 4 into minus 2. So A value I got it as 1. So how many X plus 2 ions are present? 1. Where they are present? Tetrahedral voids. Actually, how many tetrahedral voids? 8. Because CCP, 8 tetrahedral voids, 2 tetrahedral voids on each body diagonal. Out of 8 tetrahedral voids, only 1 is occupied. Remaining 7 are vacant. So percentage of tetrahedral voids occupied. So there is only 1. 1 is occupied out of 8. So what is the percentage? 12.5 percentage. So yeah, let us move on to the next question. So the distance between, this is also a simple question. The distance between adjacent oppositely charged ions, rubidium chloride, potassium chloride, sodium bromide, potassium bromide. Data is given and all are having which structure? NaCl. And he's asking distance between oppositely charged rubidium bromide. Simple solving equation procedure. Very simple. NaCl structure, right? So adjacent oppositely charged ions means these two you have to take. So whatever the given value, that is radius of cation plus radius of anion. So the given value is radius of cation plus radius of anion. Very simple. Solving equations. What do you want actually? What do you want actually? Rubidium bromide. So you take rubidium. Right? Clear? You also need bromide. Yes, you take bromide. Either this one or this one. Okay, no issue. You take either this one or this one. No problem. So for example, if I take this one. So rubidium chloride plus potassium bromide. Rubidium chloride plus potassium bromide. But there are also we have chloride ion and potassium chloride. You can subtract it. No problem. You can also subtract. So let us see how to develop this equation. See, for example, if I take KBr and KCl, there are so many ways actually. There are so many ways, but 100% you will get the correct answer if you do it correctly. Correct equation if you have taken. See, for example, KBr I have taken and I'm subtracting KCl value, so that here what happened, this one gets cancelled and I'll be getting, so bromide ion radius minus chloride ion radius is 15.4, right? What is our requirement? Rubidium bromide. So here now rubidium bromide. So I have taken rubidium chloride and this one. Already told you there may be some other way to solve, but same answer you'll get. So again this will be cancelled. So you'll be getting 343.9. You just use the logic. Very simple. You have to use the data properly and you have to use the equation properly, right? And the next one. The solid AB has a rock salt type structure. If the radius of cation is 200 picometers, then what is the maximum possible radius of anion? Maximum is asking. So radius of anion will be maximum if radius of cation is minimum. That logic I'm using. And here rock salt type structure means which void? Octahedral void. What is the range of octahedral void? 0.4142 to 0.732. But he's asking maximum possible radius for anion. So for cation you have to take the minimum possibility. So minimum possibility means you need to take 0.414. Lower range you have to take. and the radius of cation by radius of anion, and you will be getting maximum possible value for anionic radius. And the next one, okay, this is repeated model, not necessary. And let us move on to some more questions here. In fact, we need to solve some questions on diamond cubic also, and the Schottky defects, Frenkel defects questions we could solve. Yeah, and of course the theoretical density, if the crystal has 4% of Schottky defects will decrease the density. And zinc sulfide, so 4 ionic pairs, we are expecting 4. And here 4% of Schottky defects, 4% of Schottky defects means what is the actual Z effective? 3.84. Theoretical is 4. Because of Schottky defect, Z effective what happened? Decreases. So if you take the ratio, and actual density will be 0.96. Theoretical density is given as G, and actual density will be 0.96. Density decreases due to Schottky defect. And the next one, in a crystal at 827 degrees centigrade, 1 out of 10 power 10 lattice sites is found to be vacant. Out of 10 power 10 lattice sites, 1 is vacant. At what temperature? 827. At 927 degrees centigrade, 1 out of 2 into 10 power 9 lattice sites is found to be vacant. And the question is, find enthalpy of vacancy formation in kilojoules per mole. Somehow you have to use enthalpy vacancy formation. Some atoms are leaving the solid, so the bond is breaking. Somehow you need to use Arrhenius equation. So at 827 degrees centigrade, in 10 power 10 sites, 1 vacancy. If you take 1 mole, how many vacancies? So that is Na by 10 power 10 per mole. That is the formation of vacancy at 827. At 927, the temperature is increased, rate is also increased. So here 2 into 10 power 9, in every 2 into 10 power 9, 1 vacancy. And if you take 1 mole, how many vacancies? F2. And a simple Arrhenius equation you have to use. So Arrhenius equation means in chemical kinetics, rate constant, the same procedure, log K2 by K1 is equal to delta H by 2.303 R, T2 minus T1 by T1 T2. So here this is at higher temperature, this is at lower temperature, and here I'm finding this delta H in kilojoule per mole. So R value is 8.314 kilojoules, therefore into 10 power minus 3. So one is 1200 degrees, 1200 Kelvin, another one is 1100 Kelvin, temperature difference. And after this, a simple simplification process, we'll be getting 176.9 kilojoules per mole. So once again, I'm telling you, I will not waste time for simplification part. All right, procedure I have to give, more number of questions I have to cover. That is my strategy. So a quantity of 80 grams of salt XY of a strong acid and a weak base is dissolved in water to form 2 liters of aqueous solution. 80 grams of salt of XY, it is a strong acid and weak base dissolved in water. See, you need to underline 2 liters. The pH of the solution is found to be 5 at a room temperature. If XY forms a cesium chloride type crystal, and the radius of cation and anions are 160 and 186.4, so anion is bigger, so anion will form simple cube, cation will be in cubic wide. Which of the following are correct? Kb, weak base he mentioned, no? Kb value also he gave. Avogadro number he is asking us to take 6 into 10 power 23 and root 3 value. So let us first understand the question. You have taken a salt of formula XY of 80 grams. You prepared 2 liters of solution and the pH was found to be 5 at room temperature, and the solid has cesium chloride structure and that is the given data. Of course, cation and anion radius also given, and Kb is also given. Now, what is the molar mass of the salt? But no, we have to find actually. Okay, let us first find whether it is 100 or not. See, he gave salt of strong acid and weak base. So you need to recollect ionic equilibrium concept. At room temperature, pH is less than 7. The solution is acidic in nature. But in some other chapter, of course, I will help you in proving all these things. So pH is equal to 7 minus half pKb minus half log C. That is a salt hydrolysis concept. Which ion undergoes a hydrolysis? Which ion undergoes hydrolysis? Here it is a salt of strong acid and weak base. So cationic hydrolysis. And pH is given. And pKb I have calculated because Kb is 4 into 10 power minus 5. pKb is 5 minus log 4. 5 minus log 4 means 4.4. And from this, I am finding concentration. How much concentration you are getting? 0.4. And you have volume. What is the volume? 2 liters, not 1 liter. Volume is 2 liters, right? So here, this is the concentration, molarity. So the weight of the salt, formula weight of the salt into 1 by 2 volume of the solution, and formula weight of the salt I'm getting 100 gram per mole. And what is the option he gave? 100 gram per mole. So this is correct. Degree of hydrolysis of the salt. Degree of hydrolysis of the salt. Already told you which hydrolysis? Cationic hydrolysis. Do you know how to write the reaction? So this is cation. It undergoes hydrolysis and gives XOH and H plus. What is its concentration? C. How much part undergoes hydrolysis? CH. So remaining C minus CH. This is CH. This is CH. So H plus ions concentration is equal to CH. What is the pH given? 5. pH is 5 means H plus ions concentration will be 10 power minus 5. Concentration we have just calculated 0.4. And the degree of hydrolysis will be 2.5 into 10 power minus 5. So 2.5 into 10 power minus 5 is the degree of hydrolysis we got. So what is the given option? Let me check. If it is 2.5 into 10 power, yes. So this is correct. And unit cell edge length we have to find. And after that, density. Which solid he said? Cesium chloride type. And cation is smaller in size according to the data. Since it is cesium chloride, I have taken body diagonal. So this is corner, and this is body center. And this body diagonal is equal to root 3a. So 2 times of radius of cation plus radius of anion. This information is given in the question, and you are getting edge length 400 picometers. Correct. And can't you find density? What is the Z effective one? What is the molar mass? We got 100. What is the edge length? 400. A cube volume. So you'll be getting density. So the density will be 2.6 gram per centimeter cube. So the answer is ABCD. Right. So here, these are some models I tried my best to discuss. And of course, there is no end for this. We can create so many questions we can create. But the thing is, the logic you have to catch. So what is the logic, and whether you are in a position to link the given data or not, you have to check. And yes, and this is the end of this video. Not only this video, in fact, this is the end of solid state series. And shortly, I'll meet you soon with some other chapter. Thank you very much.